But this means that the commutators are trivial, starting from the second particle space on. So in some sense, these are the simplest probability measures, because they will give very little non-commutativity. Okay? Then we have this, these are the Gegenbauer, I think, polynomial associated to the beta distribution. And we have the negative binomial. You see again, the negative binomial, what the negative binomial has in common with the gamma. You see, you recognize from the principal Jacobi sequence. Again, is quadratic. See, as I told you, the class, the Gaussian is characterized essentially by the growth of omega n like n, and the Meixner, non-standard Meixner, are characterized by the growth like n squared. Nobody knows what kind of measures appear when you have a growth like n cube. Okay? Okay, now I gave you, I wanted to show the commutation relation for the uniform. You see, in the commutation relation for A daga, for the uniform, you get a negative commutator, negative constant. And it's because I was wondering at the beginning of the theory, if the commutator, in quantum mechanics, the commutator is positive definite, because A daga is 1. And in multi-dimension is the delta Aj, which is a positive definite function. But this is a very nice counterexample, and I want to propose you an exercise to say, so it's very natural to, since we know that the gamma is the commutator being a constant, essentially, if I go like omega, my omega n grows like n, the commutator goes like 1. So if it grows like a constant, a sigma times n, sigma is the variance of the Gaussian, then the commutator will go like Gaussian, is a constant. But the covariance is positive, strictly positive, unless you have the delta. What happens if, so you may ask yourself, this is a problem I invite you, it's not so difficult, but it's nice. The problem is this, what could be the anti-Gaussian? Which kind of measures have the property that the commutator is constant, but it is strictly less than 0? And you can do it, the exercise is not so difficult. Of course, you have to have some experience in this manipulation with orthogonal polynomial. If you have experience, it's easy. But if you are newcomers, it may be difficult. However, if you don't succeed, you tell me and I will show you the proof. You can prove that if this is true if and only if the associated probability measure has a finite number of atoms, which depends on the number of atoms depend on the constant C.
Finite number?
Finite number of atoms is an atomic measure concentrated on a finite number of points of R, and this number depends on C. Okay. So now we come, can we put it up? Now we come to the fundamental, no. Now we come to the main, the theorem that we had no time to discuss last time. Namely, so last time we have shown that if we have the polynomial algebra, we have a state, we say we give a probability measure, but state is more general. So we have a state, and if we have the state, we can associate the two Jacobi sequences. If I have the two Jacobi sequences, I can define the orthogonal polynomial sequence by the induction relation. Remember, we also make always the convention that phi minus 1 is also the vector 0. Okay, now, you may ask, you see, the Jacobi analog of the moment problem. In the moment problem, given a probability measure, you have the moments. And you ask, if I give you a sequence of numbers, when this sequence is contained, is the sequence of moments of some probability measure, and there are very well known. You can ask the same question for this. So if I give two sequences, omega n and alpha n, when these two sequences are the Jacobi sequences of some state on the polynomial algebra. So, given two sequences, omega n and alpha n, when does there exist a state phi on the polynomial algebra such that when I apply the orthogonalization procedure, I come back to the omega n and phi n. Okay? And I want to give you a proof of this, which is very it is devised in such a way. This is the famous, very well known in the literature. It is called the Favard lemma. Okay, remember that there are necessary conditions only on omega n. Only on omega n. The fundamental condition is this: omega n equals 0 implies omega n plus k equals 0 for each k. Of course, we are in the real numbers, the natural numbers. Okay. Now we want to understand what is the situation. So what we give a quantum proof of the Favard lemma, which gives you a good intuition of what we will do in the multidimensional case, which is more difficult. You will see why. Okay, now how to do it? Start from the quantum decomposition. You know that X is a quantum decomposition as creator plus preservator plus annihilator. Now, let us look at this condition in a trivial equivalent way. You have that A dagger is equal to X minus A0 minus A minus. Now, suppose that I remember in our condition, in our theorem, what is given? Is given omega n and alpha n. They are given. And I want to reconstruct the measure, the state of the polynomial algebra, okay? So we will do it in two steps. First, we reconstruct the scalar product. And then we use the theorem that we proved yesterday, that the scalar product comes from a state if and only if the x are symmetric. So we first reconstruct the scalar product, some scalar product, using omega n and phi n. And then we prove that this scalar product is such that the multiplication by x is Hermitian operator, is equal to adjoint with respect to the new scalar product that we have constructed. Okay? Now, in the language of what is this equivalence in the language of orthogonal polynomial, is simply this: phi n plus 1 equal x minus well, in fact, x phi n minus alpha n phi n, not minus, plus, minus is minus alpha n minus omega n minus 1 phi n minus 1. Now, this written in this way, the Jacobi relation suggests you naturally an inductive procedure to construct this scalar product. You see, because suppose that I have constructed all things up to n, and that I know these are given. So I know for every k, omega k and alpha k. But x is a purely algebraic operation. It's independent of alpha k, alpha n and omega n. So I can use it. And this automatically will give the n plus 1 polynomial. Let us see what happens in the first step of the induction. Start from 0. If we start from 0, we have this condition. So this is 0. So we have that phi 1 is x phi 0. Phi 0, remember, that is the identity, minus alpha 0 phi 0. Okay? So I have a phi 1 as a vector. Now, phi 1 is a polynomial of degree 1, and therefore is independent on phi 0, because remember that phi 0 is multiplication by the constant 1. So they are harmonic polynomial of different degrees, so they are linearly independent. Okay? So, if I define the vector space multiples of phi 1, and I add, of course the intersection is 0, because we said they are linearly independent. So this is a direct sum in the vector space sense with phi 0. And I know that this direct sum must be the polynomials of degree less or equal than 1. Okay? Because here I have the constants, and here I have one monic polynomial. But monic polynomial of degree 1 means x1 plus constant, as you see here. So I subtract, and I get the two monomials, so I get all polynomials of degree less or equal. Okay. So I have the space, let me call the space, since it will be important for us, we give a name. So this vector space, we give a name P1. Okay, now, since, remember what are our data? Our data are omega n and alpha n. At the moment I have only used alpha 0. Why? Because since phi is the identity, the norm of phi 0 square is phi of 1, which is 1. And once I give the norm of a vector, I uniquely determine the scalar product in the space of the multiples of this vector. And this scalar product is nothing but, if I take two numbers, u, complex numbers, u and v, the condition that the norm is 1 of phi0 is 1 uniquely fix the Euclidean scalar product on the complex. So the scalar product of phi0 is uniquely defined by the norm. But in the proof that we gave, we had the recurrence relation for the norms. We had the famous formula that the norm of phi n minus 1 is equal to omega n plus 1 times the norm of phi n. So again, this is a necessary condition. Therefore, if I want to solve the Favart problem, I must define the norm of phi1 as omega 1 norm of phi0, but norm of phi0 is 1. So the norm of phi1 is a necessary condition. Given omega n, it must be omega 1. But if I give the norm, by the same argument I used here, the scalar product is uniquely defined. So I now have a Hilbert space P1 with a scalar product 1. And the scalar product is just defined by the same argument, only that the norm, instead of being 1, is omega 0. Sorry, is omega 1. Okay? It is clear, the argument. Now, so I have a one-dimensional vector space. And now I impose the condition that P1 is orthogonal to P0. So now, due to the fact that this sum is a direct sum of vector space, I obtain that I have a scalar product on the polynomials of degree less or equal than minus 1. Because this condition, plus the fact that I have the scalar product of P1 and the scalar product of P0, uniquely defines that scalar product on their orthogonal sum. And this sum becomes orthogonal with the new scalar product. Okay? Now, now that I have the space P1, so I can define an operator A daga bar 0, which takes a vector in P0 and brings me to the vector phi1 in P1. So this is the definition. I define A daga 0 of phi0 is by definition phi1. And since you have now this from P0 to P1, we want to prove that this operator has an adjoint. But if it has an adjoint, this adjoint must satisfy A daga phi0. And because of orthogonality, we are in a space of 2 dimensions. Because of orthogonality, A plus is phi1, so it can only be non-orthogonal to phi1. I have to put phi1 here. So the adjoint should, this is A bar 0. So this should be a certain operator, bar A minus bar 0, acting on phi1 of phi 0. Okay? phi1, and the scalar product must be calculated by the space of phi1. So I know that this is omega 1. But phi 0, sorry, no, this is correct. But phi 0 has 1 unit norm. So I can write like this. So, since omega is real, I can bring inside, it's positive even. And so you see, from this and this, you obtain that A minus bar 0 applied to phi1 is equal to omega 1 phi 0. And if you remember the definition of annihilator, this is the necessary condition that we found in our definition of the Jacobi, of the annihilation associated to a certain Jacobi sequence. Okay, now you understand how we proceed. So we have constructed what? We have constructed various objects. The first one and most important is from 0 to 1, we have constructed the vector, the new vector, the new information. Then, using omega 1, that is the Jacobi sequence, we have defined the scalar product. And we have also defined the space P1. We have defined the space P1. The space P1 is the space of multiples of phi1. Then we have imposed orthogonality. Then we have defined the operator A daga bar 0. And then we have proved, now no longer defined, but proved, because we have the scalar product. We have proved that the adjoint of A daga 0 in the sense of the scalar products 1 and